This video is the first of our Chapter 19 videos. This accompanies our first worksheet dealing with alkanes and isomers. In this chapter, Chapter 19, we're going to get an introduction to organic chemistry, which is, we're going to talk about what organic chemistry is in a little bit, but we're going to talk about different classes of organic compounds, their structures, how to name them, how to draw them, and what types of properties are going to result. This particular video, we're going to focus on introducing organic chemistry, and we're going to talk about our simplest type of organic compounds, which are our alkanes. So if you were in class, we would have gotten together in groups and discussed what organic chemistry is. And so we often brainstorm. People often talk about organic chemistry maybe being related to living materials. So we often relate organic to maybe things growing. Oftentimes we're connecting organic to things like in the grocery store, that things are grown naturally. And organic chemistry was initially related to or founded in the study of living materials, what was making up living materials. However, organic chemistry actually goes beyond that. It's not just the compounds that make up our bodies or make up the plants around us. Even though it is, and it's very important, it's also broader. It encompasses, the materials in the clothing that you're wearing, the gasoline that you use to get to school, some of the foods you may have eaten, natural or not. And what we find is in common with all of these things is that the foundation of their molecules consist of carbon and hydrogen. So that's the requirement to be an organic compound. We've got to have carbon and hydrogen. Now, organic molecules do not contain only carbon and hydrogen. Some do, but we also come across many. They're going to contain oxygen, nitrogen, sulfur, phosphorus. We could have any of our halogens connected to it. But the foundation, again, is that carbon and hydrogen. And one of the important things, again, with organic chemistry is that it is the foundation of living things. It's what makes up the compounds in our bodies. But it also makes up a lot of the materials in the world around us. So living organisms contain millions of organic molecules. And in addition to that, there are more than 67 million organic molecules that have been made in laboratories. So why? Why are there so many different molecules out there? What's so special about carbon that such an array of different molecules can be formed from just a handful of elements? And one of the key things we've got to think about, we've got to go back to our first semester chemistry when we learned about our dot structures for our particular molecules. Remember that when we dealt with carbon always formed 4 bonds. Something that forms 4 bonds we describe as being tetravalent. So carbon is tetravalent. It forms 4 bonds. Now, in addition to forming 4 bonds, we can bond to other atoms, so other carbon atoms. We could bond to, again, oxygens or nitrogens or sulfurs or halogens. When we form those bonds could be single, double, or triple bonds. The consequence is that when carbon bonds to other carbons, each of which could form 4 bonds, they can begin to form chains or even ring structures. When we add in the ability to form different bond types, so throw in our single bonds, our triple bonds, our double bonds, throw in our other different types of atoms, the possibilities become enormous. In addition, when more than 4 carbon atoms are present, they can also form different structures with the same numbers of carbons and atoms. And when we get different structures, we're going to see in this chapter, it's going to result in different properties. Now, as a result, because we've got so many different varieties of organic compounds, it's going to be very important to have a standard organizing principle. These organizing principles are going to include classifying our compounds based on functional groups as well as molecular size. Now, a functional group, and we're going to get into those in more detail later in the chapter, it's going to be an atom or group of atoms that imparts particular chemical and physical properties. Now, a given molecule could have multiple functional groups, but each functional group results in particular properties, particular types of chemical reactions for that organic compound. Now, when it comes to size, we can classify organic compounds as being molecules or macromolecules. Molecules are going to be those substances that typically are going to have a mass less than 1,000 U. Remember, that's our atomic mass unit. So less than 1,000 atomic mass units. Macromolecules, they're going to have a mass around 1,000,000 or higher. Macromolecules are generally going to consist of repeating units called monomers. These monomers, when they start to form these long structures with these large masses, they're going to become known as polymers. So you guys have probably heard that term polymer. A lot of your clothing is going to be made of polymers. A lot of plastics are made of polymers. Your body, your proteins are essentially polymers. They're long, they're big macromolecules consisting of long repeating units. And we're going to talk about those in some of our case studies. So we're going to take a look at the simplest class of organic molecules, known as our hydrocarbons. So if we think about that word, hydrocarbon, based on the name hydrocarbon, what elements do we think are likely to be in that class of organic compound? So if we break it down, first of all, we've got carbons. So hydrocarbons are going to contain carbon. But then we also see hydro. Whenever we see hydro, hydro is connected to hydrogen. So hydrocarbons are going to be a class of organic compounds that contain only carbon and hydrogen. So when it comes to our hydrocarbons, again, they contain only carbons and hydrogens, and we're going to encounter four major classes. We have alkanes, alkenes, alkynes, and aromatics. Now, these four classes, they differ by the type of carbon-carbon bond present and the number of hydrogens present. We're going to get into detail about each of these. We can talk about them real quick. The alkanes are going to contain only single bonds. Alkenes are going to have one or more carbon-carbon double bonds. Alkynes are going to have one or more carbon-carbon triple bonds. And then our aromatics. Aromatics are typically going to consist of a ring. Not always, but generally they're going to consist of a ring of alternating double bonds. And we'll see some examples of that. Now, when we look at these, something that's going to be important is we classify organic compounds because we're going to classify them into these different types of categories. The name ending for any organic compound indicates the class of compound. So if we look in alkane, alkanes are going to have that A-N-E ending. So if we look at a name like propane, that A-N-E ending lets us know it's an alkane. Alkenes are going to have an E-N-E. Alkynes are going to have a Y-N-E. And then our aromatics are going to be a little bit different. They're often going to have an E-N-E ending. So we're going to start in this chapter by taking a look at alkanes. So here we've got several structures for alkanes. We've got methane, CH4, ethane, C2H6, propane, C3H8. Now if we look at the structures in this image, and these are some common hydrocarbons, we're asked to look at these structures and identify what they have in common in terms of types of atoms, types of bonds, and their names. So if we look at these, if we look at the types of atoms, the atoms are all carbon-hydrogen. If we look at the bond types, they're all single bonds. If we look at their names, we've got methane, ethane, propane. They all end in that A-N-E ending. So these are all our alkanes. Alkanes, N and A and E, they all have the single bonds between our carbons. Now, alkanes are described as being saturated hydrocarbons. So if we think about that word, you should be familiar with the word saturated. What does saturated typically mean? And so when we talk about saturated, you may remember from solutions, saturated meant it was full of solute, it had the maximum amount of solute. Oftentimes, if we describe something as being saturated, it's full, it can't contain anymore. That same terminology applies here. If we describe an alkane as being saturated, it's full. Now, when we say full, specifically, we're talking about full of hydrogen. That saturated alkane has the maximum number of hydrogens. Each carbon. So carbon will always have 4 bonds, but in this case, being saturated, the 4 bonds maxes the carbon being bonded to 4 atoms. So each carbon is bonded to 4 atoms. And the way that occurs is through those single bonds. So a saturated hydrocarbon has the maximum number of hydrogens, maximum number of bonded atoms, and it's achieved that through having only single bonds. Now, alkanes all share the formula CnH2n plus 2. We can use this formula to determine if something is an alkane, or we can use it to determine the formula for an alkane. So if we look at an example for the structure of propane, without even drawing that structure, we can tell the formula C3H8 is an alkane. The way we can tell this, we can look at the number of carbons to determine N. So we have 3 carbons, so our N value will be 3. So then we look to see if we have the appropriate number of hydrogens. And so what we're going to do, based on this formula, the H2n plus 2, we're going to take 2n plus 2, and we're going to see if it equals the number of hydrogen we have. So 2n, so 2 times 3, our number of carbon, that will give me 6, plus 2 gives me 8. So C3H8 has the proper number of hydrogens so that all of my carbons are full, and we have an alkane. So if you look at our next problem, we want to write the formula for an alkane that contains 8 carbons. So we're going to use that same formula. We're going to use that CnH2n plus 2. So if I've got 8 carbons, that means my N value is 2. So I've got to figure out my number of hydrogen. Hydrogen is going to be 2 times N, so 2 times 2. Oh, sorry, let's go back. N is 8, so 2 times 8, which will be 16, plus 2 gives me 18. So my formula, I'm going to put my 8 as my subscript on my carbon, and then my hydrogen will be 18, so C8H18. Now, our next problem, we're taking a look to see if the formulas that are provided represent alkanes. And we're going to determine why or why not. So if we look at C6H12, so here I have an N value of 6. Again, we're looking to see if we have the appropriate number of hydrogen. So my hydrogen should always be 2 times my number of carbon plus 2. So 2 times 6 will give me 12, plus 2 should be 14. So looking at this, my formula has 12 hydrogens, but to be an alkane, we're supposed to have 14. That means this is not an alkane. It is a real organic compound. It's just one of our other classes of hydrocarbons. And so we'll do the same thing with our C4H10. So my N value is 4. My hydrogen should be 2 times 4 plus 2. So 2 times 4 would give me 8, plus 2 is 10. So this time, I have 10 hydrogens. An alkane should have 10 hydrogens. So C4H10 is the molecular formula for an alkane.